I'm recording the lesson as we go through it. And I'm going to be recording it with all as the lesson progresses, so you can see the way in which the sum progresses. So I want to see how it goes, so bear with me. So I've just started off like that so people can see the notes at the beginning. And here's the first example. So this is the sort of situation that we can set up. We want to find the Cartesian equation of this plane. It's passing through a particular point, and it's got the normal 4, 5, and 6. So we know that we have, let's just get a nice kind of pen. We know that we've got the point A, which has the positional vector 1, 2, 3. Actually, it's not a capital A, is it? It's a small a. That's our positional vector for that point that we've been given on the plane. We've also been given the normal, which is this vector 4, 5, and 6. What was the normal equation for the plane? It is r dot n is equal to a dot n. And what is r? R is some arbitrary point on the plane with coordinates what? X, Y, and Z. So you know how when you form the equation of a straight line, you need a point in the gradient, don't you? And you go y minus 1 is going to equal 3/4 x minus 2, whatever the case might be. Okay, you're taking that point, that arbitrary point somewhere on the plane, to be able to generalize the situation. So we're going to be doing the same sort of thing here. R dot n, the dot product of these two. What are we going to get with that? Right.
4x plus 5y plus 6z.
4x plus 5y plus 6z. Yes. That's what the start of the equation is going to look like. I've then got to look at the dot product between my point that I have on the plane and the normal. Tyler, what's that dot product going to be? Yeah?
4 plus 10 plus
So 4 times 1 plus
10.
2 times 5, which is 10, yeah, plus 6 times 3, which is 18. Whoopsie. Six times 3. So, what do you reckon that is? 32. And there is the equation for that plane. How can we test it?
Use GeoGebra.
Yeah, if you don't have the GeoGebra going with us, you put that point x, y, and z into it, it'll be a point that lies in the plane. Now, how can we find another point that lies in the plane? Well, there must be some point where x is 0, isn't it? And maybe there's a point when y is 1. In which case
17 over 6.
we're going to get 6z is going to equal 32 minus 5, isn't it? Is it?
Yeah.
Yeah, minus 5. So we're going to get z will be 27 over 6. 9 over 2. That's another point that lies in the plane, because it will satisfy that equation for the plane. So just as we can test whether a point lies in a line by substituting into the equation of the line, so we can test whether we can get points that lie on the plane. Now there are heaps of them. And we're going to come back to this at a later stage. We're going to need to be able to find points that lie on a plane. And we sometimes use that sort of version over there. But this is the important thing that we've got over here. there's the equation for our plane. Any questions with that? Okay. Right, well, let's move on then and say, right, find the coordinates of the point of intersection of the line r is equal to I plus k plus t 2i plus j minus 3k with the plane 3x plus 2y plus 4z equals 11. I don't particularly like working with equations of lines in that format over there. How can I rewrite it in a vector equation type way with a column in column format? 1, 0, 1, thank you. Plus t 2, 1, negative 3. So there's a line on the plane. We want to know where it's not a line on the plane, it's a line. And it's going to be cutting through the plane at some point. How can we go about finding it out? Finding out that point of intersection.
Put r equals to 1 plus 2t, t, and 1 minus 3t, and substitute the x, y, and z into...
Alright, so we're going to look at this vector r in terms of x, y, and z, aren't we? Is that what you're saying, right? Yeah. So, what do we know? In fact, it's going to be 1 plus 2t, that's what your x value, that's how your x value can be written. We know that the y value can be written as t, and the z value can be written as 1 minus 3t. So we're expressing any point on that line in that way in terms of our parameter t. And once we've done that, where can that go?
Solve for t.
Solve for t. How are you going to solve for t?
I'll put it into the...
Okay, we're going to substitute into the equation of the plane. So I'm going to have 3 times 1 plus 2t and plus 2 times t plus 4 times 1 minus 3t. And all of that's got to equal 11. And now, as Ray says, we've got an equation in terms of t. We need to solve in terms of t, so we can say 3 plus 6t plus 2t plus 4 minus 12t is going to equal 11. How many t's we got? Negative 4t is going to equal 11. What have we got here? 3 and 4 makes 7, so it's 11 minus 7. So minus 4t is going to equal 4. Let's get a bit more space on the page there. And so t is going to equal minus 1. All good and well that t is equal to minus 1. How do we use that? Plug it back in, okay? We know that x was equal to 1 plus 2t. We know that y was equal to t, and we know that z was equal to 1 minus 3t. And so it will follow if t is equal to minus 1, that x is going to be minus 1, y is going to be minus 1, and z is going to be 4. So, the point of intersection will be minus 1, and 4.